Okay, well, welcome everybody. It is 12 o'clock and we are going to get started. Want to thank everyone for joining us today. We are recording this training and we'll make this available afterwards. Uh, First off, I want to, of course, welcome everybody to this inaugural Passive House training webinar. Thanks to Eversource, a proud sponsor of Energize Connecticut, for making this training available at no cost. So my name is Mark Pignatelli with ICF. I'm a senior manager and I've been working in the energy efficiency industry for about 15 years. And we just launched a really exciting training program focused on Passive House for Connecticut professionals. And I recently worked on a very similar offer in Massachusetts that has been very successful. So really excited to be here. We also have Anna Zylik from the ICF team. Anna's been really integral in the Massachusetts training and is going to also be helping to lead the charge here in Connecticut. So just a couple quick housekeeping items related to the training today. So obviously we're using the Zoom platform. We do encourage folks, if you do have any questions, please use the Q&A button on your Zoom window as opposed to the chat window. We will be monitoring questions. We'll try to answer questions as we go. And we are hoping to have some time towards the end to answer questions towards the end. We do have a pretty full presentation here today, so if we are not able to get to all your questions today, we will follow up and try to address those after the training. A few other items just to mention here. Everyone is, of course, on mute. This goes till 1 p.m. today, so we have about an hour to get through quite a bit of really exciting information. Just to share a few other things regarding the Passive House training offer in Connecticut, we will be doing several more trainings moving forward over the next 2 years, year and a half, 2 years. And we do have a really great offer for any folks that are interested in pursuing Passive House accreditations, whether through FIAS or PHI, so Certified Passive House Designer, Consultant, and alike. We are really excited to offer a 50% cost share towards the expense of those trainings and certifications. Again, thanks to Eversource. So our email address is at the bottom of this slide. Please feel free to reach out. And Connecticut Passive House is also very involved here, and there's information going out in their newsletters too. So with that, I'd like to introduce two board members from Connecticut Passive House. Really excited to have George Penniman and Leonard Wyeth here to present today on Passive House 101. Just to give a little context, George is a licensed architect, CPHD. He's been practicing architecture in Connecticut and Rhode Island for the past 30 years, leads a 5-person firm in Essex working on projects throughout New England, has a passion for high performance building, and currently serves on the board of Connecticut Passive House, as I mentioned. His Passive House Ash Point Cabin in Maine has been featured in several publications and won Connecticut Green Building Council's 2017 Out of State Award. So really cool work that George has been doing. And Leonard has over 30 years of experience, and his work displays his deep creativity and resourcefulness. His firm Wyeth Architects projects have included new houses, renovations, restorations, interior design, landscape design, space planning, site planning, campus planning, as well as institutional, corporate, and urban design. Recently completed project Stonington Passive House won CTGBC's 2018 Passive House Honor Award. So we have two distinguished guests here. Let's get things started. And I will just add one more thing. As you can see from my background, I'm over the moon with the turnout. We have over 200 people on the call today. We had close to 500 people register, so I have a feeling we'll have more people trickle in. So this is great. Looking forward to some more trainings. And with that, I will hand it off to George to get us rolling here. So thanks for joining, folks.
Terrific. Thank you, Mark, and thanks for everybody for tuning in. And thanks to ICF and Eversource for sponsoring this educational series to support and promote the Passive House building standard throughout Connecticut. As Mark mentioned, we are board members of Connecticut Passive House. It's a group founded several years ago to offer Passive House resources, education, and outreach using the broad knowledge base and skill set of our peers. We want to engage with all members of the building community vendors, general public, and everybody, and advocate among our legislators to promote Passive House as the most effective tool we can employ to make a significant impact in global carbon reduction while increasing occupant comfort and health. We encourage you all to become members, which will give you a chance to be kept apprised of our events, our post-COVID site visits we have planned, trainings and opportunities throughout New England, as well as to promote your own work through our website and share in this growing community. Today's presentation aims to give you a very broad introduction to the Passive House Building Standard, what Passive House is and isn't, its 5 key principles, and how, when applied together in a rigorous methodology, they result in buildings with a huge reduction in energy consumption and heightened occupant comfort. It assumes minimal prior knowledge of Passive House, and we'll try not to venture too deep into the weeds, but we hope that it will spark interest in acquiring knowledge and taking advantage of the great opportunities that are offered through this Eversource initiative. In 1991, a physicist, Dr. Wolfgang Feist, expanding on work that had been going on in Canada in the 70s and 80s on super insulated houses, set out to design a house without heat, a pretty radical concept. The result was this 4-unit townhouse, of which he occupied the end unit, and he fitted it out with data acquisition systems to test his objectives and theories about how this could be accomplished. From this experience, he developed the Passive House methodology, a proven, measurable, science-based system to drastically cut energy consumption. In the 30 years since, thousands of passive house structures have been built all over the world. Dr. Feist is a brilliant physicist, but not a great branding professional. The chosen name has caused some confusion and perhaps hindered its growth and adoption, and hopefully we can clarify any of those misconceptions in the next hour. As the following slides will show, Passive House principles can be incorporated in multiple building types and styles across the architectural spectrum. It's obviously relates to single family houses and can be a very contemporary design, such as this one in Washington State, or more traditionally designed single family houses, such as one right here in Connecticut. Passive House is being used more and more for affordable housing, multifamily housing in Connecticut, like this project, and throughout New England and the country. Passive House works for office buildings. This is the headquarters of the Rocky Mountain Institute in Colorado. All over Europe and increasingly in the States and in New England and in Maine especially, Passive House buildings are being constructed as schools with obvious benefits for the inhabitants and for the long-term benefit of the communities in which they belong. And institutions of higher education, colleges and universities who build for the long term always are increasingly building their new projects to the Passive House building standards. This is a dormitory at Williams College. But Passive House can also be used for churches. It can be used for infill urban housing, such as this project where old brownstone was renovated in Brooklyn to Passive House standards. And it doesn't have to be low rise. More and more high rise office buildings and apartment buildings are being built to Passive House standards. This is the residential tower at the Cornell Tech campus on Roosevelt Island in Manhattan, 26 stories, 352 apartments, all built as a Passive House structure. And finally, on the books now, and I think close to starting construction, if not started already, the Sendero Verde project in East Harlem, which is a mixed-use affordable housing complex, which could become the largest Passive House project in the world at 709 units, a school, a community service space, public gardens, and retail. So we come up against a lot of myths and misconceptions about Passive House out in the world and even among the profession, among architects and builders and engineers. such as that it's only houses, which the previous slides have dismissed. People assume that it's highly insulated and airtight. It must be stuffy and you can't open the windows. All of these things are untrue. Expensive, no, upfront expense, but quickly made up by reduced mechanical costs and savings over the life of the building and utility costs. People assume that a building that has reduced the energy consumption down to near nothing must be too complicated, and a very smart house full of sophisticated wiring and sensors and things. That's not true at all. A smart house type thermostat in a passive house will just die of boredom because all it does is monitor a stable temperature with very minimal variation. And finally, that it's only suitable for temperate climates. Passive houses are being built in the far reaches of Canada, uh, in our country, Minnesota, Maine, cold climates, as well as in Australia and the southwest of the states. The realities are that passive house does not sacrifice comfort for energy efficiency. It provides increased comfort and increased health benefits, as well as increased resiliency at the same time as providing up to a 90% reduction in heating and cooling demand over average existing building stock. It provides additional energy security by providing minimal utility costs, especially in affordable housing, where often the residents are trying to balance paying the electric bill or paying for the heat versus paying for groceries. By reducing the minimal utility costs, that burden is reduced on those families. As I mentioned, the cost upfront for a more robust building envelope quickly offset by reduced mechanical requirements and a short payback. And it is the best path to get to the goals that we're trying to achieve in the next few years, the Paris Accord, Architecture 2030, and within our own state, the Connecticut 80 by 50 targets. In some cities, passive house is now the building code in Brussels, Belgium, in Vancouver, in Canada. This is the way you have to build. They're taking the long view. So what does define a passive house? There's a short little video here that tries to answer that question in 90 seconds.
Passive house explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist in Austria, Dr. Feist, built the first passive house. Here's what he did. 1. Proper insulation. It's just like wearing the right winter jacket, it also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out. Add all these things up, and it turns out your house doesn't need a heater or air conditioner. So where does the heat come from? A passive house needs 90% less energy, and that can easily be supplied by your body heat, the sun, your appliances, light bulbs, and even your TV. This saves you a lot of money on your heating bill and helps preserve the environment. Did we make it in 9?
Well, you don't need to see that twice.
Passive house.
It's important to understand that passive house is a performance-based standard. It's not prescriptive. It doesn't tell you exactly how to achieve these goals. It is performance-based, and it's validated through energy modeling, a few different software packages that can be used. It's validated through the strict standards and protocols that are applied to certain elements to get a passive house certification, such as windows and ventilation and mechanical equipment. Construction details are verified, tested, time tested, and vetted by passive house Institute. And finally, on site, you're validating your own performance through blower door testing, excuse me, and ventilation system commissioning and sign off. So we get to the 5 principles which were alluded to in the little video. The 5 basic principles of passive house construction include thermal insulation around the whole building envelope, thermal bridge reduced design, passive house windows and doors, airtightness, and finally an adequate ventilation strategy. We're going to touch on each one of these 5 principles very superficially over the next few minutes. The first being insulation. So why do we care about heating in buildings? That's kind of a silly question. Obviously, we want to stay warm when it's cold out, but we should understand that space heating accounts for a huge majority of the energy consumption. This is just an example of what it means in New York State, space heating as a percentage of total energy consumption. In the US, across our whole country, buildings consume 48% of US energy and contribute 45% of US greenhouse gas emissions. According to the Sierra Club in New York City, buildings are responsible for 67% of the emissions. And that makes real estate the city's most polluting industry, ironically. So we need to try and reduce all of these things. And in a passive house building, we do it through obvious ways. We increase the R value and the robustness of the building insulation system. There are dozens of ways to do this, varying materials with different degrees of effectiveness and R value per inch, which comes along with different degrees of environmental consequences. Again, passive house doesn't tell you what you have to use or even how much. You just have to use enough to get to the standards to certify your building at the end of the process. Typically, though, a single family home in our zone for passive house might have an R60 roof, R40 in the walls, and R30 in the floors or under slab, with the obvious benefits of reduced heat loss in winter, reduced heat gain in summer, and often overlooked but very important for humans' comfort are the interior surface temperatures. If we provide a thick enough envelope, these interior surface temperatures are not much different from the temperature inside the center of the building. So you're not aware of changes in temperature and drafts and increased discomfort. So this infrared photo sort of shows what we want to have, what we want to see, and what we're trying to avoid all in one. It's a picture taken in winter of a street front in New York, 5 buildings, one of which has been renovated to passive house building standard. The other 4 are existing. Maybe there's been a little insulation thrown in there at a certain point. But by the degree of red and yellow in the photograph, you can see that these buildings are just draining heat out into the street. They're all acting like mini radiators up and down the street, warming the street front, but losing heat from their interior. The passive building, on the other hand, has surface temperatures that are similar to the air temperature, the outside, so indicating that no heat is escaping those buildings. When we think about how we're insulating these buildings, we need to think about the wall cavity, and the key word there is cavity. A lot of contemporary framing and engineering for buildings requires more and more wood studs, and this is an example of a kind of a wall that makes a passive house adherent start to break out in a sweat. It's just a highway for thermal bridging and all heat to be drained out to the exterior. Plus, it doesn't allow any space for insulation within that wall cavity. So there's a few different options that we could pursue. Just one of many strategies is a double stud wall, a simple framed wall with conventional framing on the outside for added insulation, or a structural framed wall on the inside with a truss joist set up to have the added depth that allow for the continuous insulation blanket. All of these methods are standard framing, just not something that a framer does every day, but certainly not that much to ask to get the benefits. We have to be considering the exterior insulation so that we get that continuous wrap of insulation around the perimeter of a building and minimize any opportunities for thermal bridging. That can be accomplished with exterior foams or some more benign environmentally materials such as a wood fiberboard product. This one is imported from Germany, but there's now a old paper mill in Maine being converted to produce this in the States. So hopefully we'll be seeing a lot more of that readily available on the market. And in masonry construction, obviously masonry is a terribly conductive material, poor insulator. So we have to keep that exterior wrapped with a continuous insulation of an exterior insulated finish system or some kind of insulating blocks, which then can be stuccoed or cladded over in some form. You have to think about the roof and how you're going to get added insulation in your roof. And one strategy in wood frame construction is with a raised heel truss, where your truss is designed so that you get that continuous 16, 18, 24, however many inches of insulation your project requires, that can run continuously over the top plate of the wall, guaranteeing that there's insulation blanket wrapping your building. And we have to think about foundations and footings. Obviously below grade, we're using a lot of foam to do that. There are other products coming online that are available, such as a Roxel product that can work under a slab, a product made of spun recycled glass material, which works as an insulator as well as a sub-base for your concrete slab. So there are many materials and strategies. Again, it's not prescriptive, it's all performance-based. And that segues us into the second principle, which Trip will describe for us, thermal bridge-free construction.
All right. I assume that's out there. Does that appear right on the screen?
Yep, looks great.
Thermal bridge free. Let's face it, some materials conduct heat a lot better than others. Obviously, steel is a lot better conductor than fiberglass insulation. However, wood, for example, is also a pretty substantial thermal bridge. The notion is very simple. The more thermal bridging there is, the more heat loss there is in the envelope. So you can imagine that all thermal bridges by whatever material, it affects the amount of energy required for heating and cooling. It's a condensation and moisture problem related issue, and there's thermal discomfort. Basically, thermal bridges are bad. This is a photo of a building next to my office. You can see exactly where the insulation is in that roof, and you can see exactly where it isn't. But note the depression in the snow above each of the roof rafters. There's enough heat escaping out of that the snow is melting rapidly underneath, the layer underneath. It's a significant heat loss issue. The thermal camera, one of the better devices known to man right now. Here's a building that looks like a nice uniform envelope, but look at the quality of the windows. Obviously, they're not holding heat in at all. Look at the floors engaging the front wall there. Large amounts of heat escaping there. Imagine for a second balconies on a high rise. They're like fins on a fin tube radiator. They're leaning out to dissipate heat. This is a shot upward at balconies sticking out, and you can see the large amounts of heat from the center of the building, which is otherwise pretty well insulated, being fed right out to the cold night air. I'll take an extreme example. I really, really like this building, the Aqua Tower in Chicago. But notice that the architectural expression of these particular balcony-like structures that extend out past the thermal envelope, notice that they get denser towards the top. Chicago is known as the Windy City, and there's more wind up there than there is at the street level. So what does this look like from a thermal camera's viewpoint? Looks like a really effective heat radiator. It's also not necessary. Available now are structural foam blocks of such high compressive strength that they're very good insulators, not just thermal breaks, but very good insulators between exterior steel and interior steel. And this is equally true for columns. Their compressive strength is more than adequate to handle that. I just wanted to throw this example out because we've all seen buildings like this. It's a developer housing project of structural slab, where the slab is extended out to the face of the building and expressed. And it's done that way for purely economic reasons. It gives a platform on each floor to build up the CMU, some XPS foam insulation, and then some brick with metal studs and sheetrock on the inside. But look at the thermal bridge of that slab extending out there. No matter how you cut this, that slab is going to be cold on the interior, cold enough, in fact, for condensation, even frost and ice to build up on really cold winter days inside the building. Another example of the floors really are effective radiators out to the outdoors. And you can probably imagine when I snapped this photo driving out of New York, I'm not sure who did the building, but the amount of energy that's escaping through a structure like that. I wanted to throw this photo in. The building on the left, across the street there, is a housing block, and the insulated walls are not really containing the heat very well, and the windows are really bad. They're allowing plenty of heat out. But the building on the right is actually built to passive house standards. You can see, as far as the camera is concerned, it's not picking up heat coming through the insulated walls at all, and the windows are allowing much less heat out. That little burst of energy in the upper left corner, the window is cracked open and the occupant is smoking a cigarette. So what about the windows? We've been taught from the start that windows are compromised. I mean, think of it as an ideal. If you had an enclosure that had no windows or doors, it was just a beautifully insulated box, you'd have a heat loss ideal. 68 degrees inside, 0 outside, no leaks, no drafts, no problem. Well, almost no problem. If you're claustrophobic, there might be a big problem, but you might find it dark and depressing. You might find it, or have a perception of no fresh air at all. But by golly, it's a good thermal envelope, and it'd be easy and cheap to heat and cool. But if we have to have windows, okay, let's just throw in a single glazed window to make a point. 0 degrees outside, single glazing, even if it's fixed, you're probably going to have surface temperatures below 40 degrees, so that the air temperature on just the inside layer of the glass is going to be above, barely above the 30s. So the consequence, of course, is you've gained natural light and views. You've got fresh air now, assuming that it operates. You can use it as an extra escape, that's good, or throw a chair through it if you have to. But you're going to pay more for heating and cooling, and you're going to have a situation of condensation and frost on a window like that. The additional problems include convection, a cycle where the 68-degree air gets close to that cool surface of the glass, it cools rapidly, falls, and creates a good sized draft on the bottom, displaces the lighter, warmer air and creates a cycle. In other words, a constant draft along the lower level. Not only that, of course, but as we all know, there are two types of heat. There's convective and radiant. Radiant is only line of sight, and it's directly from a warmer surface to a cooler surface. So if you have a bare arm, for example, in a situation like this is where even in the center of the room, you feel goosebumps on the exposed arm because the heat is leaving the body so quickly. So in this situation, you have limited choices. You can kind of put a scarf on the guy, better boots, and suck it up, or deal with some mechanical solutions. But let me address the condensation for a second. Here's a double glazed insulated window in a northern climate. It's clearly cold outside. It's had multiple hits of cold, if you will. The outside is a sheet of ice down along the lower portion, and the inside is a sheet of ice along the lower portion. A couple of things to note. Note that in the middle of the glass, there is not a condensation problem. And remember that all of the American manufacturers will give you an R value of their windows in the center of the glass. This is a great example of the center of the glass is usually not the problem. The problem has to do with the thermal bridge around that perimeter. That's an aluminum spacer and in this case, a PVC frame. It conducts heat so effectively that you end up with situations like this. Now, don't get upset. I know you haven't looked at a psychometric chart since high school or college, but this is just to make a point. It's looking at 68 degrees inside and 20 degrees outside at 30% relative humidity. The dew point's at 35 degrees Fahrenheit. At 50% relative humidity, it's at 49 degrees Fahrenheit, and at 60% relative humidity, it's 54 degrees Fahrenheit. So rule of thumb, if you want a window that will, in our heating zone, not suffer any condensation, it has to perform effectively enough so none of the interior surfaces, either on the glass or the frame, fall before approximately 60 degrees. Obviously, higher is better. So we'll circle back to that. Let's go look at the mechanical solutions to historically the problems that we've seen in the past. Put a radiator under the window to counteract the falling cooler air so that that convective fall is counteracted by a heat source. And what you're doing is mixing the air at that point. You're not actually getting rid of the drafts. You're taking the edge off them, if you will. You're also creating a kind of radiant heat source that counteracts some of the radiant loss to the skin directly to the cool surface. But you can also put up a curtain or some kind of any object in between you and the window, but now you've given up the view just to stop radiant heat loss. And you've still got the drafts, you've still got the radiant loss, you've got a sense of cold, it's still costing money to heat, and you still have the problems of condensation and frost. Just because it's important to calculate into the formula. Summer and winter heat. Obviously, if you don't control the summer or winter heat gain, especially the summer, you can get into a cooling problem, which is easily solved by a bigger overhang. So that's easy to control. And you try to maximize, obviously, the winter sun because the heat helps you in that circumstance. But you still have the need for the radiator for nighttime and cloudy days. You still have the infiltration, radiant, convective losses. You still have the condensation and frost. High performance windows, if you can put a window in that actually does perform where all parts of the interior, meaning the glass, the frame, and the installation, are at 60 or 62 degrees Fahrenheit, a couple of things happen. Obviously, you've solved the condensation problem, but you've also eliminated the need for the heat source under the window, because at 62 degrees, you don't have a draft inducing energy fall to the floor there, and you're not cycling the air in the room in any kind of significant way. So by increasing the performance of the window frame and installation to that level, you start having a ripple effect. Notice that the interior temperatures are now at worst 62 to 68, and it stays more in the comfort zone. At some point, the windows can actually be a net gain, and this can make the client particularly happy. You think, I'm going to change metrics here. The numbers you see are in kilowatt hours per square foot per year, but the metric is simple at face value. A loss is a negative, and a gain, a plus, is a positive. Let's take the example of an R30 wall on the left. A wall, no window, no door, just the wall. Even just a wall, you see a 2 kilowatt hour per square foot per year loss. And remember, this is measuring over a year's time. And into that wall, we stick an Energy Star casement window. In other words, R3.3, overall R3.3. Now we've gained the view, the light, and we gain in the sunny days, we gain a plus 11. But we're still losing minus 18. In other words, we're losing more than we're gaining. So we've gone from a net loss of 2 to a net loss of 7 by that window. But let's flip the formula here. Let's put a window in that's R, say 5.3 overall. Now, everything upends. It's almost counterintuitive. By the improvement in the window, including the films and the orientation, we've boosted the gain from plus 11 to plus 14 and dropped the loss from minus 18 to 11. And we end up actually gaining energy in the building. In fact, it means the window is better than a wall without a window in the big picture. The window can perform better than the wall. So what makes a high performance window? Triple glazing, the right coatings. In other words, coatings selected for orientation. Certain coatings help reflect heat. Certain coatings help retain heat, and their careful selection is critical. Gas-filled insulating units. The frame needs to be highly insulated, and we'll have a slide for that. And the overall unit, the R value has to be as high as possible. The inverse is, of course, saying it's a low U value. The insulated glass edge can't be aluminum spacers. It can't be a good thermal bridge. It needs to be something that actually insulates. So rather than aluminum, having a warm edge spacer, something that is a material that will actually serve the airtight needs and not transmit thermal energy. In other words, you need to think of the whole picture, not just the center of the glass. It's got to be the glass, the frame, and the installation. And the installation has to be good enough that you can actually measure the performance after the fact. This is just 3 images to give a feel for it. These are Passive House certified windows. You can get the sense of, in the center one and the one on the left, the number of air chambers which are helping as insulators. The double and, in fact, triple seal, air seal in the opening and closing portion of it. And the edges, which are in an insulating material on the glass, are actually sunken more deeply into the frame. And foam, where it's used as both reinforcement and insulating, is basically in line with the glass. The window on the right actually works equally well. That's got an aluminum exterior portion, a thermal foam, a rigid or structural foam component in line with the glass, and regular wood on the interior. The item number 4, airtight. This requires an example. So let's think of this as a generic building. And to make all the calculations really easy, we'll have a 2-story building that's 32 feet square, 18 feet tall, and a 45-degree angle on the roof. No windows, no doors. And to make the calculations even easier, we're going to say that the walls, the floors, and the roof are all R50. This is not a high value. By the way, I'm led to believe that the 2021 Energy Code is going to, on its prescriptive path, is going to require roofs be R60 minimum. So before we talk about air, we need to talk about heat. The heat transferred through the envelope, just the envelope. So make the calculation and you come up with 7,192 BTUs per hour. 7,192 BTUs per hour. I want you, please, to remember that number, or if you can't remember the whole number, just remember 7,000. 7,192 heat loss just through the structure. So what about infiltration? So let's get rid of the walls, the roof, and the floor. And the green symbolizes the volume of air in the center. Green chosen because that's the symbol for putrid stale air, I guess. We calculate the volume of air in this and make a series of assumptions. And you remember this from school, I'm sure. Specific heat of air, specific density of air. Density in this case is determined at sea level. We're doing this in British thermal units, BTUs, which I'm sure you remember 1 BTU is about the same as the heat given off of 1 burning match. And of course, heat travels from warm to less warm. There's no such thing as hot and cold. There's only heat and lack of heat where calculations are concerned. So the amount of heat, 1 cubic foot, gives us the per cubic foot infiltration rate. And so 1 air change per hour on our little example would be 28,091 BTUs per hour as compared to 7,000 and change for heat loss through the structure. It's considerably larger. But consider an old New England house. It is not at all unusual in a New England house to see 12 air changes per hour. In fact, seeing much more is very usual. A 5-bay colonial with a center chimney, you can't even, by blower door, get a reading on the air changes per hour because so much air comes and goes from the chimneys, as well as all the older methods of construction. But 12 air changes per hour, which is not unusual, would be 337,092 BTUs per hour. So imagine if you want to heat this building, this 2-story building, you would have to assume that your heating equipment would have to have the capacity to do at least this much plus the heat loss through the outside. So 337,000 plus another 7,000. Okay, I'm going to cover a bunch of things quickly. We're in climate zone 5. So that's our reality here. Now, it was in 2009 that the International Energy Conservation Code introduced for the first time any reference to air changes. And the magic number they used was it needs to be less than or equal to 7 air changes per hour. 2009, first reference. So 7 air changes per hour in our example would be 196,637 BTUs per hour. That's better than 337. Then in 2012, the International Energy Conservation Code reduced the number to less than or equal to 3 air changes an hour, which would bring it down to 86,703 BTUs per hour. It's better, but it's not great. 86,703 BTUs per hour is a big number, especially when you compare it to the very small number that's escaping through the structure. So any discussion about energy conservation, any discussion about sizing equipment really is centered around how many air changes per hour does your building actually have in real life. The fewer the air changes, the better. The maximum allowed air change for a passive house is 0.6 air changes per hour. Now, less is even better than that, and anybody working on a passive house is going for a considerably smaller number, but 0.6 is the maximum allowed. And that brings the heat loss down to 16,854 BTUs per hour. Notice, still more than twice the loss through the envelope. So consider, if you invest in the high R value for walls, roof, and floor, and you invest in the air sealing, you move the load down considerably, massively, 90% or more. And all of a sudden you're able to have much smaller heating and cooling equipment, much smaller, 90% smaller, which can be a significant cost, certainly significant space, and certainly a massive energy savings. George, I'll pass it back to you.
Thank you, Trip. So we've now, through Trip's good work, have created a highly insulated building envelope. It's airtight with reduced thermal bridges. It's got high performance windows oriented for maximum solar gain in the winter and shaded in the summer. We now need to address the fifth principle of passive house building design, which is the HVAC systems. With passive house, it's more about ventilation than heating and cooling. It's about balancing loads, offsetting the heat loss through windows, building envelope, and ventilation with the gains generated by solar gain, appliances, equipment, and people. And it's important to remember that in New England, as much as we would love to, we still have to provide some supplemental heat. What the fifth principle specifies is that you have to do this with high efficiency ventilation with a greater than 75% heat recovery. I'll explain what that means shortly. But basically, in designing the house and doing all the calculations, you line up the losses on one side through ventilation, windows, cellar floor, wall, and roof, offset by the gains on the other side, solar gains and the internal gains that we talked about from people and dogs and cooking and anything that could generate heat within the building. And if we've done it right, we've reduced the need for additional heat to 4.75 kBTU per square foot per year as the heating demand. If we've designed our building correctly, we maintain year-round comfort because we no longer have, as Trip was discussing, the heat supply below a window, which is radiating cool air into the space and creating convective currents and draft pockets and different temperatures from one side of a room to another. Because we've done all that, we now free up the perimeter wall. We've got our thick insulation. We've got our windows, which keep the interior surface temperature above 62 degrees, so that we can move all the heating and ventilation to the inside of the building and leave the perimeter free for bigger windows, for furnishing, and just for greater comfort. What we do is, how we do this is with heat exchanger, an HRV, heat recovery ventilator, or an ERV, an enthalpy recovery ventilator. And these will provide balanced ventilation year round. In the old days, we would turn on an exhaust fan in the kitchen or bathroom, which would depressurize the whole house, or you supply intake air only and you're pressurizing the whole house. What we need to do is provide this exhaust and supply in a balanced form. And the way it works with the HRV is that continuously fresh air is drawn into the building, it's filtered, comes into the heat exchanger, where it passes by but does not contact directly the exhaust air being expelled from the building. That exhaust air transfers its heat to the incoming fresh air, and it has to do it at 75% efficiency at a minimum, meaning that 75% of that exhaust air's heat is transferred to the incoming air. And currently you can get on the market HRVs with much higher, in the high 80s, low 90s percentage of heat recovery. So now that fresh incoming air has been tempered and warmed up as much as possible, it can pass through another supply of heater coils to bring it up to temperature if desired, or we can provide that additional heat necessary through mini splits, ducted or not ducted, or other heat pump, or some kind of heating strategy. It's up to you. But the main point is that this air is now circulated throughout the house constantly, 24/7. Fresh air is introduced into bedrooms, which is critical for healthy occupancy, to avoid CO2 buildup while people are sleeping. And it's supplied to living areas of the house or building. And it's extracting air from bathrooms, from kitchen, and any other spaces that are suited for exhausting air. And that gets taken out. It works, as I said, 24/7 to provide a wonderfully comfortable interior environment. And basically, in a nutshell, that's it. For us who are passionate about this, passive house building standard is a win-win-win solution. It's an obvious win, as we just discussed, for indoor comfort, eliminating pollutants from outside, as well as constantly flushing the interior air and helping to rid your interior space of bacteria, pet dander, radon, et cetera, et cetera. It's airtight, providing that ventilation 24 hours in a highly efficient way. It's the energy consumption of these ERVs is minimal. And it's also guaranteed through third-party testing, so that you know that you're occupying a space that's been through this rigorous protocol. It's a win from an investment point of view. You're adding value to your asset, and you're also getting a guaranteed return on your investment. As utility costs increase over time, you're getting that savings over time, and that just compounds. On the other hand, if you try to go reduce your first costs and build a less robust building, you may save some money up front, but you're going to have ever increasing operating costs. So it's basically a deferred expense. And finally, it's a win as a step towards greenhouse gas reduction. This chart is mostly interesting to me and for our purposes right now with the bottom row here, which describes energy consumption in terms of gallons of oil per square foot per year for a typical single family home. Before the days of the oil embargo, a house was was burning 7.9 gallons of oil per square foot per year. In 2003, the new energy codes drastically reduced that by half, but we're still burning 4 gallons of oil per square foot per year. An Energy Star home, which is a pretty good way to build a house, is still burning 1.3 gallons per square foot per year. But finally, passive house is down to 0.4 gallons of oil per square foot per year. So passive house is about comfort, it's about health, it's about resiliency, and it's about energy conservation. It can be accomplished with materials and methods that we're already using in construction. We know how to do this. It's nothing outrageous. We just need to work to make assemblies more robust and pay extra attention to how we detail and construct them. So I just would like to say thanks for everybody for listening and your interest. I hope this gets people excited to up their game by continuing the series of workshops and events that will continue throughout the year. And Mark is going to jump in and have a couple more announcements about those events and workshops. And then we have a few minutes for some questions.
Yeah, thanks, George, and thanks, Leonard. Great job, guys, getting through a lot of material there. And but yeah, we did want to just promote a few upcoming events. We have the Connecticut Green Building Council NESB event coming up March 25th, 26th. So check out nesb.net for details. Really exciting conference to check out and continue the learning here. If you want to go to the next slide. We have a couple dates we want to bring to your attention. So we're doing a 4-part building science workshop with Stephen Winters Associates. You can see the dates, times, and workshop titles below. We've also been promoting this through the Connecticut Passive House newsletter. I would recommend checking out the Connecticut Passive House website and signing up for their newsletter. But we will be continually promoting these workshops. So really excited to be announcing these future workshops, and there'll be more to come as well. So I think we can go to the next slide. Yeah, so again, just want to thank everyone for taking the time today. We had a really great turnout for this first training, so super excited to have everyone listen in. Hopefully this was valuable. Thanks again to Leonard and George for really offering up your expertise here. Contact us, Passive House Training, ct@icf.com. Anna and myself and our team are at the ready if you do have any follow-up questions or anything in particular regarding the training offer here on behalf of Eversource. So with that, we can open it up to Q&A. We do have just under 5 minutes left, so we got quite a few questions coming in. I'm going to do my best to try to get through a couple of these and pass them over for Leonard and George to try to address, and we'll see where we get. I don't think we'll be able to get through all these. So we do have a question here around just residential high performance technologies that are becoming more available, and has Passive House organizations vetted these technologies such as hydronic heat pumps, vacuum insulating, glazing, and high R-value paint? Leonard, George, any comments on that question?
The various heat systems, air-to-air heat pumps, various hydronic systems and what have you, some are Passive House certified, some are seeking Passive House certification, and some are just not. If somebody wants to use a system that is not certified by Passive House, it can be done. It just requires the going through a somewhat extensive process to prove that whatever the claims of the manufacturer for performance are actually are. In other words, there's an incentive to use products that are already certified. Does that?
Yeah, and I think they don't just pick products to vet and certify. I think the manufacturer has to apply to the PHI or FIAS to gain certification for a specific product.
Yes.
Great. Another question here is asking if there are any good guides for homeowners who are doing renovations to get closer to Passive House standards. I will say I know Passive House Institute does have an EnterFit standard for this type of work, but Leonard, George, anything in addition there?
Yeah, the EnterFit standard is a really good approach for existing construction that otherwise it's very difficult to take an existing building and bring it up to Passive House standards. Not impossible, but it's very difficult. So there's a renovation standard. It's called EnterFit. It allows a little more flexibility in certain performance characteristics, being realistic to the market out there. You can find information on that on the various websites for Passive House International, PHI, or Passive House US, PHI US.
Yeah, thank you. Great. Another question, excuse me, is kind of centered around, what is also included in Passive House certification. So maybe we could even just touch on some of the QA/QC protocols, kind of that journey of going through and becoming certified. A lot of the comment here too says, a lot of great ideas, good designs. this can all be implemented, evaluated, but what about getting certification? What's the benefit there?
One that's actually a three-pronged question there. By getting certification, you've actually demonstrated that you've designed a certain standard into the building and then proven that you've met it. In the case of a client of ours for a passive house that was an entirely new construction, they really wanted to be as close to off the grid as they could reasonably. So we designed a passive house for them with photovoltaics on it, and their monthly electric bill seems to be $9.11 for an entirely electric structure, 2,700 square feet total. And the reason it's $9.11 is because that's the minimum transmission charge for Eversource. So, obviously a client like that didn't want to get close to the standard they wanted to get there. And so getting it certified is you start the process at design and then follow it all the way through. That was one way to assure it. Now, it is also true that by applying once experienced with it, applying passive house standards, you don't have to get certified in order to either meet the standard or get close to it. But if you want to prove it, getting certified is a good reason.
Great. So we are right at time. We could, George, Leonard, if you want to take a couple more questions, I'll defer to you there.
I'm good for a couple minutes more.
Okay.
Maybe 5. Trip, I don't know.
Yeah, no, go for it.
Okay. Great. Yeah, we still have a good number of folks on. So do we have any incremental cost data or approximate cost to become Passive House certified? So of course, that could be a little bit of a multi-pronged question as well, but maybe if we provide like an example of incremental cost, I'm not sure if you have anything handy, guys, to share.
Can I insert something before George dives into that?
I don't have any costs on hand, Trip, so that's all yours.
I just want to note that one of the questions came up had to do with project tours, and asking if there were some passive house buildings that could be toured, experienced, if you will. The answer is yes, once the COVID-19 situation allows safely, the tours will commence. But during the current situation, Connecticut Passive House won't be running any tours until it's a more safe environment. But once it's a safe enough environment, Connecticut Passive House will be running tours on as regular basis as possible. Jumping at the price, let me approach that differently. Virtually every architectural project has a different, there's no way to give a generalization on price for anything. However, here's what we've discovered. The very first time a contractor builds a passive house, they're on a very steep learning curve, especially where air sealing comes into play, thermal bridging and what have you. They need to do things and think of things differently than they've traditionally done them. And anything that causes a contractor to swerve laterally means they're going to spend more time fussing with it, which translates to more cost. However, what we've also discovered is once they've done it once, I will use the example of you install a passive house window in a very particular way to assure that the installation meets all the energy standards of the actual unit itself. Once they've done it once, the first time they do it, it's a time-consuming, kind of irritating experience. But from that moment on, they're never going to install a window any other way for anybody. So from that moment on, it doesn't cost any more. we're finding that as the market adapts to the building techniques that get you where you need to go on the 5 principles, that we're not seeing increased cost. I've heard it justified numerous ways, including, yes, triple glazed windows cost more than double glazed windows, but then the heating system is so much smaller that you end up saving money, just as a gross example. Does that begin to answer it?
I think that helps. Yeah. I will say, I know there's been some data out there pertaining to some Massachusetts projects, the Mass Clean Energy Center. They did they had like a competition essentially. Feel free to reach out to our Passive House inbox. We could certainly point you towards some of the data that they found with incremental cost. I think in the end, it wasn't huge. It was actually pretty reasonable. But I think to Leonard's point, there's a learning curve, with this, and as builders and folks get more comfortable, you'll see that these costs can be pretty comparable to a code built project. So just scrolling through, I think I'll try to take one more. It looks like we have hit on several of the questions. We had a couple repeat questions throughout. There were some questions around air tightness and ventilation, especially in the days of COVID. I feel like George did a nice job speaking to that in terms of indoor air quality and health and comfort. So I don't think we need to go there. Let me just take a look here.
I'll jump in with a
Please.
couple questions. We're questioning about our claims about solar gain through windows, and obviously that depends on if the window is positioned so that solar gain is possible. And just so people understand that when you're modeling a house through the energy modeling software, every elevation of the building is treated differently, and every window in the building is analyzed as per how much direct solar gain will be on that window. So it's very precise, and that's where most of the work in the passive house design comes in, is the precision with which you analyze each surface of the building based on orientation, etc. And in the summer, you're supposed to be thinking about how those windows, which let in so much great solar gain in the winter, how those are shaded and what your overhangs are, and whether you're providing additional overhang, et cetera, et cetera. So go ahead, Mark, sorry.
Great, no, that really helpful. And well, I think we should probably wrap up. I will say there's been a few questions I've seen here kind of around the difference between a building certification versus like a professional certification for an individual. And then of course there's Passive House Institute US, and there's Passive House Institute, which is an international standard. So I would encourage everyone to take a look at both of those websites, FIAS and PHI, to take a look. They have different professional standards available. This is what I mentioned earlier, where this program on behalf of Eversource can cover half of your cost to become a Passive House certified professional. So definitely check out those websites. Feel free to reach out to us directly, and we can certainly point you in that direction. There's a lot of upcoming trainings through FIAS and PHI. So we're happy to kind of help point you in the right direction there. But I do think at this point we're at time. I really appreciate everyone hanging in an extra few minutes here, and just a great turnout. So super pumped to have you all join. And again, want to thank Eversource, and Energize Connecticut. Looking forward to keeping up the momentum with future trainings here. And thanks again to Leonard and George. Your time was really appreciated, and your expertise. So yeah, we're really hoping to help build and kind of develop the workforce in Connecticut to get more familiar with Passive House, start to see more professionals become accredited, and certainly see more buildings become certified. So Leonard, George, any closing thoughts on your end?
Take advantage of this great opportunity. Thanks. We're
Yes.
so excited that it's being made available.
Yes, absolutely.
Yeah.
Hey, Mark, thank you. Anna as well.
Yeah. No, great. It's great to be here, and yeah, looking forward to working with Connecticut Passive House even more. So Thanks again to everybody. Happy Friday, and have a great weekend. We'll hopefully see you soon
Okay.
on the next trainings.
Take care. Thanks.